We're going to be talking predominantly about digital images. And so from here on, we're going to talk about this kind of image for the rest of the image characteristics section of the lectures. So digital images are symmetrical. They consist of rows and columns that define n number of pixels. So it's a grid. Multispectral images, by their nature, are composed of more than one band, with each band being sensitive to a different part of the spectrum. And then the bands are geometrically registered to each other. That means that, the same pixel, the lower left pixel in the top layer is at the same location as the lower left pixel in the next band, et cetera, et cetera, et cetera. So we refer to, in a multispectral image, no matter how many layers it has, we refer to those as bands. When we talk about images, we talk about 4 resolutions, okay? And they're all illustrated here. One of them are spectral resolution. That's basically the number of bands that an image has. One of them is spatial resolution. That's the area on the ground represented by a particular pixel in the image. So you might have spatial resolution of 5 meters. Okay, so that means that each pixel on the ground covers 5 by 5 meters. We have a radiometric resolution, which I will talk about later. And then we have temporal resolution, and temporal resolution is just the amount of time between regular acquisitions of an image. So radiometric resolution has to do with the brightness values that can be recorded. So for instance, in a particular image, you're going to try to record everything from the darkest pixel that you can observe to the brightest pixel you can observe. And between the absolute dark and absolute light, you have a number of levels of gray. Okay, so if you look at that image, the two figures to the right, you have brightness values. So that's often what we would call, from computer terminology, 8-bit, which means there are 256 possible levels that it can be recorded. And then on the right, it shows the grayscale from darkest to brightest. And this has changed. Early sensors might have only had 64 levels of gray that they can record. For a while, the standard has been 8-bit data, which is this 256 grayscale levels. AVHRR has 10 bits of resolution. We'll talk about AVHRR later in the semester. So it's 1,000 grayscale levels. And AVRIS, a very sophisticated sensor, has 16-bit resolution for 65,536 grayscale levels. So you're able to make much finer detail measurements, and so you can find finer differences between different surface characteristics. And there's just a little figure pointing out the basics of how radiometric resolution works. I'm not going to go into this any further. So spatial resolution, the area on the ground over which spatial information has been collected. Again, as I showed you with this picture of a lotus flower, and then we've magnified it so we can see individual pixels. Within the image, you can reference a particular pixel using file coordinates. So you could say it's in column 3, row 1, as it is in that little figure on the lower right, or you can use map locations if the image has map information associated with it. So you could say, show me something at 105 degrees west, 45 degrees north. Um, this gives you an idea of the variety of pixel sizes available. This is um, uh, These are images from the H.J. Andrews Experimental Forest in Oregon. It's a Doug fir western hemlock forest. On the upper left, you have images from a sensor known as MODIS. Those are 500 meter pixels. On the upper right, those are pixels from a sensor known as the Landsat Thematic Mapper. Those pixels are about 30 meters spatial resolution. And then on the lower left, I'm showing you an ADAR image, which was an airborne system, 1 meter pixels. You can't really see 1 meter pixels though in that image. So then I've blown up that little square area so you can see how much higher resolution it is than either the 30 or 500 meter resolution images. So MODIS and similar things would be considered to have coarse resolution. Images with small pixels like ADAR are considered fine resolution. This gives you an idea of the changes that occur as you go from fine resolution in the upper left-hand corner to coarse resolution in the lower right. And one of the things you see is that at the edges of that building, you get more of a sort of a stair-step effect. You don't get smooth edges. You get, jagged edges. So the factors responsible for spatial resolution, scale of the imagery, the imaging geometry. So the closer you are to an image, the smaller the area of the image that you or area that you record. The resolving power of the sensor. So you might have film shown there on the left with either fine grain or coarse grain. That's going to affect the spatial resolution. The digital camera, you might have a low density focal plane with large pixels or a high density focal plane with small pixels, and that will follow into the spatial resolution of your image. So chromatic spectral resolution, so that's one band, usually either through the visible or possibly through the visible and the near infrared. Those often have the best spectral resolution. Thermal is often the worst, and that has to do with the amount of energy there is in the visible versus the thermal. If you think back to the black body curves for various wavelengths, you know that there isn't a lot of thermal energy being emitted by the Earth. There is a lot of reflected visible light, so you can use finer pixels and still keep up a relatively large amount of energy in the panchromatic versus the thermal. Another factor responsible for spatial resolution is the characteristics of an object and then the background in the atmosphere. Objects smaller than an individual pixel can show up if they're much brighter than the background. And this is, if you see, the smiling face was created during some sort of celebration, and everyone was given a yellow umbrella. But you can see this as well as you can because it's very different from the background. And so it tends to dominate the individual pixels, and that allows you to make an image which can then be captured by an overflying satellite. These two images show the impact of atmospheric and lighting conditions on spatial resolution. You can see that the left-hand image, which was taken under good conditions, you can make out finer details. Particularly, look at the grid that is in the area where the planes are parked. It's very distinct at the left, which is under good conditions. Very difficult to see at the right under bad conditions. Now, high spatial resolution is sort of a mixed blessing. And a high spatial resolution, small pixels, those images are generally associated with a small extent, because you can kind of imagine that there's sort of a uniform amount of data for a single image, but you can either have a large extent and coarse pixels, or you can have a smaller extent and fine pixels. And this just gives the area of sampling for some different sensors. So AVHRR on the left, which is a wide swath. I think it's like 18 or 180 kilometers. I'm sorry, 1800 kilometers. Whereas on the right, you've got a Landsat TM image. That's much higher spatial resolution, but it only captures a very small area. And then even smaller for the spot sensor and the QuickBird sensor, which have higher resolution still. For film images, for digital images, we characterize spatial resolution using the pixel spatial resolution. That is the size of one pixel on the surface. With film images, we don't look at the individual pixels, we look at the scale. So the scale is just the size or distance of an object, or between two objects on the photo, and then the distance on the ground. So if you work with maps, you know scale. The most popular map scale that is used for USGS topo sheets is 1 to 24,000. That means that 1 inch on the map is the same as 24,000 inches in the real world. Distance on the photo, distance on the ground. So if it's 1 centimeter on the photo, it would be 1 kilometer, for instance, on the ground. 1 kilometer is 100,000 centimeters. So if you have an image where 1 centimeter on the photo is equal to 100,000 centimeters on the ground, your scale is 1 to 100,000. And then some people use scale factor to describe scale, and that's just, you take away the 1 to, in 1 to 100,000, and you just get 100,000. Scale comparison. So a scale of 1 to 50,000 is larger than a scale of 100,000, because that fraction, 1 over 50,000, is greater than 1 over 100,000. The way to remember this is that objects on large scale imagery are larger than objects on smaller scale imagery. And photos from airborne sensors can have variable scale because the platform altitude can be variable. The higher up it is, all other things being equal, the coarser the pixels, and therefore the smaller a pixel will be, or an object will be, on an image. Got a couple of nice little tables that Aronoff puts in. This one shows you the spatial resolution you need to evaluate the presence of various different military targets. They can also be used for civilian objects as well. Another table showing you, for a variety of imagery types, the spatial resolution of those images and the coverage, the swath width that can be captured with those various sensors. And in general, it shows that as you go to higher spatial resolution, you get lower image swaths. We're going to talk about the utility of various spectral bands. So each band is sensitive to a different color. So we have one recording blue, green, and red. And again, this is what's going to allow us to make some of the identifications or determinations that we will with multispectral remote sensing. So commonly used spectral bands. I start with UV. Most UV is absorbed by the ozone layer, but some objects absorb UV and re-emit or fluoresce visible light. And specialized UV sensors can be used to map oil spills because it reflects a lot of ultraviolet. Other than that, it's not very popular. Blue sensor, blue sensing band. It has high water penetration, but it's also highly scattered by the atmosphere. And it can be used for analysis of water characteristics, water depth, and mapping of subsurface features. It can also be used for water quality assessment and coastal zone mapping. Green can be used for vegetation mapping and health. It's got moderate penetration of water, and it's not as impacted from atmospheric scattering and absorption. And I should say that here, when we talk about scattering, we're talking about Rayleigh scattering, so which affects the blue and the green much more than the red. So red can be used for chlorophyll identification. So it can be used to map vegetation types and plant health. It can be used to delineate soil and geologic conditions. And it's the visible band least impacted by the atmosphere. Panchromatic band is a single band that covers the range of wavelengths. It's really either between 500 and 700 nanometers. That would be in the visible, or 500 and 900 nanometers in the infrared. And I should say, as we get out into near infrared and further, that Aronoff's band terminology is a little different than mine. You can see on the left what Aronoff uses, and then what I find to be more typical. So we'll be using my more typical definitions for each of the infrared areas. So near infrared is very useful. It works on, it can be used in vegetation mapping and health because healthy vegetation has high reflectance in the near IR. Broadleaf vegetation has higher reflectance than needle-leaf vegetation. Unhealthy vegetation has lower reflectance in vegetation. Clear water has low reflectance in the NIR, and turbid water has higher reflectance, and so NIR can be used to map water body extent and turbidity. Mid-infrared is useful for land cover mapping and the moisture content of vegetation because we have those water absorption features. You can also distinguish clouds and snow. And then thermal. So thermal remote sensing collects energy that has been emitted by object as a function of their temperature. And so it is also a function of an emissivity coefficient, which we'll deal with in thermal remote sensing. And so you can map objects that have contrasting temperature with their environment.